As I mentioned, I wanted to extend this class apart from what I gave you yesterday, the overview of processor architecture, which is suitable for AI. And we understood that GPUs are best suited for various reasons. I mentioned some of them, there are many more. It's not that directly you can use a GPU in AI application. There are lots of changes done to the graphics processing units, which was meant for graphics processing, and it was modified to suit for AI applications. So we will see now, not in detail because it needs lot more knowledge to know about what is happening inside. So I will cover it whenever it's needed, so we can bring in as we learn more on implementation of TensorFlow and other things. Then we can get into the details of how it is done in GPUs. This session is only to give you an overview of what is done at the graphics processing unit level to make it suitable for AI. I will take NVIDIA's architecture to explain it. Okay, I'm not saying that I'm going to give you details about what is going on inside. We will do it later. Okay. Now, I'm sure all of you are aware of NVIDIA. It is pronounced as NVIDIA, NVIDIA. This is a Latin word meaning that someone envying, being envious of something. Okay, envy. It's a Latin word. So this means that someone looking at the NVIDIA chip, they envy how it is actually performing. That's the meaning of this name of the company. It started in 1993, and the CEO who started off this company is still the CEO of NVIDIA. I have come across his interview recently, which I put the link there, which you can also read through. It's very interesting. Okay, I'll talk about that soon. So this is the symbol. This shows I. Okay, and this square means pixel. As I mentioned, pixel is the main thing about graphics, individual pixels. So that square means pixel. Now let us see use of GPU in AI. How it was started off. It started off. Okay, I'm just giving you a history. Where in 2008, almost just 12 years back, Andrew Ng is a very popular guy who started off using the GPUs for AI purposes. He was working in Stanford. He was a professor there. And he only started off to say that GPUs are suitable for deep learning. Okay. Then the rationale was that an efficient computation infrastructure. Okay. GPU has more of compute intensive elements. CPU, as I mentioned, is general purpose, whereas GPUs are meant for compute intensive graphics processing. So that has a infrastructure, means the hardware features in it could speed up statistical model training by orders of magnitude, which is nothing but our deep learning, removing some of the scaling issues associated with the data. What is the scaling issue? In AI, the main issue is the data that we need to operate on is not limited. Whereas in graphics, you know that if you have to process a 4K or a HD image, you know what is the rate at which the image is going to come. Because suppose if it is FPS, frames per second is 30 or 60, that many frames are going to be there, or 60 frames per second is going to be coming in. If it is a HD frame, you know that how many pixels are going to be there based on the width of the element and the depth, height and width. And then based on the color elements, how many are going to be encoded. Okay, it could be a 16-bit for individual R and G and P, or it could be more. So we know exactly in a second how much of data is going to be coming in for a HD processing. That is, the graphics processors are meant for processing that, but they know what is the rate at which the graphics is going to be coming, but they don't know how dynamic the image is going to be. So if you have learned graphics, the difference between one frame to the other frame actually increases the processing that need to be done. Suppose if you are having a static image and then a newsreader is only speaking, only the lip movement has to be tracked, whereas the rest of the background image is going to be the same every frame. So lots of compression is possible. Lot of processing doesn't have to be. We don't have to do any of the processing at the other end of the pixels, which are not modifying or changing dynamically over the frames. Only what is the difference in between the frames need to be communicated. So even the transmission, compression, everything becomes easier. Video transmission becomes easier when there is not much of dynamic changes happening. Whereas if it is a fast moving race or something where the whole image is moving, then it is going to be much more processing needed. So even if you include all these dynamic features into the graphics, still you can estimate how much of data is going to come for processing by the GPU. Whereas in AI, it could be much more, because if you want the AI to understand a image classification, or if it has to do edge detection or face recognition, the amount of data that is needed to train the network to make it as close as possible, as accurate as possible, is enormous. So that's where the scaling issue comes. So we need to make some changes in the GPUs so that this scaling issue is addressed. That means the data could be of big data in the AI world compared to graphics, but still we can do it if we make some changes to the GPU architecture. So Andrew Ng founded Google Brain Deep Learning, which is actually nothing but where the TensorFlow is coming from. So this is a group within Google, the company Google. They started off this project, and he only founded that, and he did the cat images recognition. Okay, he fed the DNN with lots of cat images, trained the network so that it will automatically identify cat image if it is given a new image with a cat in it. To do that, he made use of some 2000 CPUs, very powerful CPUs for performing the job. Okay. Now, this was done way back in 2008. Then they felt that it is not practical to identify one cat image. You need 2000 CPUs, dedicated CPUs, then it's not scalable. Now we cannot make it accessible to everyone. So they were looking for some other alternative, and then he teamed up with somebody Brian from NVIDIA, whether GPU can be used in that place. Instead of 2000 CPUs, how many GPUs would be needed to perform the same job? Then they identified and they found out that only 12 NVIDIA GPUs are enough to do the same kind of performance, the same kind of error in terms of identifying cats could be done. And that actually proved the theory that it is doable. Okay, that GPUs can be used for AI processing. So from that time onwards, there are other university folks who are all training using the GPUs for deep neural networks, and they also found out that it is possible to perform much better DNN implementation using GPUs. So then that time onwards, GPU became the default standard, de facto standard to use in the AI world. Okay, that's the history of, I would say, the history of GPU in AI. Okay, now AlexNet. AlexNet is one neural network which was, of course, developed by Alex from University of Toronto. He won a competition which is held by this ImageNet recognition. Okay, that's a computer image recognition competition. In 2012, he constructed one DNN and which won the competition. Okay, it's about recognizing images, and he did that using DNNs. Okay, but there were also other tools which was handcrafted software. They process the image not using the DNNs, not during neural networks. They were processing it image pixel by pixel, and then handwritten code was also there. But this DNN implementation won against these hand-coded implementations. So that is where they proved that DNN can do a better image recognition compared to other software. So they did not write any code at all. They wrote only implemented the deep learning network, and they made it learn using feeding lots of images to it. Okay, it learned by itself. They did it using NVIDIA GPU, but it was needing a lot of trillions of math operations and millions of images to be given, but it did a good job of identifying, classifying images. So this was another milestone in proving that GPUs can be used for AI. Now, I'm sure all of you might have studied about CNN in your course. I think you had a neural network course, but still I thought I will give you just very high level overview. You know that CNN is a multi-layer neural network with each of layers having multiple neurons or computing elements. What is fed to them is some input, we'll call it as tensors, or some data, is a multidimensional data matrix. These images are given or the data is given, and some computation is performed, not only one, maybe multiple, and then the output of that is fed to the next layer. So this is how the brain, our brain is actually is much more complex than what you see in a neural network, wherein we are having only layers and then the communication is only between two layers, whereas in our human brain the communication is between multiple connections may be there. It is not between only layers, but they simplified it to make sure that implementation is possible, but they perform the similar operation, and whatever the weights are given for the signal which are coming is tuned so that finally when the output nodes are giving the results, they are matching with what is required. Now, how do we train the network? We use a supervised learning by feeding in the information, what are the errors are there, and then there is a gradient descent and other algorithms to tweak this individual weights so that the result of particular feature is extracted out by multiple layers, and then finally whatever the labels we say, they are coming out as expected. So that is how we do the training, and then when unknown input is given, it gives you inference can be done based on the neural network which is already been trained on. So for training this, we need this weights to be processed properly. We needs to be fixed properly. That we need more and more images to fine tune them. So this very high level overview of what CNN is. Sorry, I'm sure you guys know more than me. Anyway, let us go forward. Unless you have some doubts, I'll stop in between to find out. Okay, now CNN is one of the deep learning methods. It is one of the deep learning methods have led to a breakthrough in the many computer vision tasks such as object detection and recognition. CNN attempts to mimic the structure of and operation of neurons in the human brain, especially visual cortex, because this is an area which is related to the viewing or whatever our eyes, okay, processing the images through the use of hierarchical multi-layer networks. Of course, it is hierarchical and multi-layer. Deep learning using CNN has been shown to be extremely effective in automating the process of learning the feature representation schemes from the training data, thereby eliminating the laborious feature engineering task. In the means hand coding the feature extraction and processing it is avoided by making it learn dynamically with a lot of images. So you don't need to code a lot. Once you fix the network, then we can fine tune it by feeding in more and more data. By using repetitive blocks of neurons in the form of convolution layer applied hierarchically across images. If you know that, at the top layer, the images edges are identified, and then more features are extracted by the next layer. Then it does a fine tuning of the features. Like if suppose you are doing a face recognition, it identifies the nose, eyes, and then mouth, and then should be smiling face. Then it identifies the individual features and then tries to identify who's the person, whether even the person's emotional state, all that can be identified. So that is multiple layers come into play, and they do different jobs at the every level. So they more and more it becomes complex as the multiple layers they go through. So it does it automatically by learning from the images, by extracting the features, and they outperform the hand coded techniques. So that's the beauty of it. It outperform the hand coded techniques. Even chess playing is no much better than the um, grandmasters now. So iris recognition, this you may be knowing, in our eyes, inside the iris is a different nerves, neural optical nerves. They form a pattern, and that identifies individually like a fingerprint. So even that is used for identifying individuals. So AI can be used, or neural networks can be used for iris recognition, and there are some proven products using this. So if you are interested, you can read this paper published in 2016. I am going to show you some results which came up in this paper about CNN, how it actually uses multiple layers to identify iris-based classification. Okay. Now, to understand this picture, this is 2010 what was done, and number of layers used in the CNN was very low, and this number gives you how much of error rate. Okay, suppose it identifies wrongly. Okay, you know the input pattern, iris pattern, to which human being it belongs to, and then actually when you feed in, it gives a error 28% of the time. It gives a erroneous classification. So that number is what is shown in the top. You can see that the classification error ratio, or a percentage, sorry, is coming down when you increase the number of layers of the neural network. So in this case, 152 layers were there, whereas these were all very small, and the improvement is not phenomenal, as you see that number of layers are increasing so much, but the improvement is only some 50%, okay, or 100%, I would say. So this is a picture showing iris classification, how it improved based on number of layers added to the CNN network. These are all different networks, okay, done by different people or using different technologies and different framework. The names of these nets show you that, and the number of the which year it was done is shown here: 15, 2014, 2013. So improvement is shown here. Okay, this is just to give you how, and these are all running on GPUs. Okay, these results were run on GPU. Okay, yeah, go ahead. I'm sorry. Yeah, go ahead. Okay, I'll tell you. Okay, let me show you this. The graph above shows the evolution of the winning entries in the ImageNet. So there's a competition, as I mentioned, for classifying different images. Different people participate. Different CNN or any neural network implementation can participate in the competition, and they will be given a standard set of images, and then they identify how much of classification, how good in accuracy of classification was done. Okay, so it was done every year. This is called large scale visual recognition challenge, organized by one ImageNet organization. Okay, now let me explain this, what is the numbers are. Since 2012, they started introducing convolution neural networks. They outperformed the handcrafted implementation of image classification with a huge margin. Okay, but they had a shallow networks. This they used earlier because the problem with earlier thing was they didn't have the hardware to run those neural networks with multiple layers. So they were having shallow layers. That means 8 layers only they were implementing it. And then you were asking about the numbers, right? It is called recognition rate, recognition error rate. That means 28% of the time this neural network recognized the images wrongly. Okay, that means you have trained it with something, and then you are giving the result, but you are not giving the label for that particular image, and then you are trying to find out whether this DNN is able to identify or not correctly or not. So if you have a shallow network implementation way back in 2010, the error rate of that network for images classifying them wrongly were at the rate of 28.2%. That means more than half of the quarter time they were classifying it wrongly. I hope you know those classification, right? So what you do is, suppose in a supervised learning we give images and labels also, and we train the network so that we know what is the, suppose number of labels are 1 2 3. If it is wrongly identifying it and you know that actually it belongs to the label 1, then what we do, we again retrain the network so that the results come as expected. So this is what is a training period wherein we give more images where we know the results and then trying to see what tweaking we need to do in the network so that the results coming out correctly. So that is a training part of it. So we can give millions of images and we know the labels. That is called supervised learning, because we are making the network learn by knowing the result of what it is supposed to give, and we use that information to train the network. In the sense, training means nothing but tweaking the different coefficients in the nodes so that the finally whatever is the output, it fires this particular neuron so that the result is turns out to be correct. Once we train it, we are going to give unlabeled unknown images which was not given to the network earlier. So it's a new image, but we know the result, but we want to see the result. What is the network trying to say? So in that case, when you feed unknown images, the network recognizing it correctly was some 28 minus 700. Okay, 28.2% of the time it was recognizing wrongly. Okay, but as you start improving the number of layers in the network, what has happened was the improvement happened. The error rate started coming down. It was able to recognize the images better, and by then the years also went by. It is not done in the same year. It was done in the later years, and then by 2015 it was done with a 152 layer implementation. The error rate was only 3%. That means it was able to identify the images, classify them correctly. I hope you understand the numbers now. Okay, thank you. So the number of layers in the CNN is shown in the graph every year from 2010 to 2015. Okay. See, don't worry about, I am just trying to tell you how now this CNN evolved and how did they, find out that the GPU is a good candidate for it. So I'm just giving you an example of that. You can read about this paper also. It's very interesting. It's not that difficult to understand, but you just get a gist of it. That is enough to get a feeling of it. Okay. So I may even, I will share it on the, along with my course material, I will share this paper also. I am not saying that I understand every line of it. Even you may not be able to, but try to understand what you can from the paper. Okay, it will be a good read. Okay, now where is NVIDIA in this game? NVIDIA GPUs are great at parallel workload. Okay, that is the beauty of it. As I told you, SIMD architecture and parallel execution of multiple data working on different ALUs. So they speed up the DNN implementation by 10 to 20x. Okay, 10 to 20x time by reducing the training iterations from weeks to days. Okay, sometimes earlier it used to take weeks. Now you can train the network in days. Okay, when I say training the network, I hope you understand. Tweaking the coefficients of different tensors coming from one layer to the other layer, so that finally what you feed in images is landing out as a particular label which is saying that it is identified how many okay, let me tell you one more thing in this in the GPU. See, if suppose you have an image, you have a DNN which is capable of identifying cats, suppose. Now you may give only a cat image here. Okay, then it may identify it is a cat. Okay, you have to say it is a cat. Now the beauty of this DNN and using GPU is you need not have to one image. It can be multiple cats can be there in your image, but still the network can identify, and then you can even, it will even identify, and then which where all the cats are found, it can identify them. So how is it done? So this requires that you need to not only process the whole image and then try to look for the cat features, even the sub images you have to be in a position to extract the cat features. Okay, so GPUs are good in that, because we normally feed in the GPUs, graphics processing unit, block by block images to it. Okay, so even the CNNs are fed like that, and even the images within that, they can identify multiple cats within the particular image that you are feeding. So CNNs are capable of doing that, training them. Okay, so let me come back. By collaborating with the AI developers, how does NVIDIA do it? They work with the AI developers. They work with system architecture people, hardware guys, GPU designers, compilers, because the tools are very important. CUDA is one good example, and algorithms, who write the algorithms, the AI algorithms. So they work with everybody and then identify the features to be implemented in the GPU, so that they can get a better performance. So they improved it by, within 3 years, they had a better performance, and it improved by 50x. Okay. Moore's law, you know that. Moore's law means when you are building a chip, Moore is one person who is an Intel founder also. He predicted that every 18 to 24 months, the number of transistors in a chip would double every 18 to 24 months. That's the Moore's law. All of you might have heard it. Number of transistors that could be packed inside a IC, integrated circuit. So this NVIDIA's improvement is much more than the Moore's law in terms of comparison numbers. So NVIDIA is having a CUDA platform. I will explain you shortly what is CUDA, and they have a different graphics or architectures to handle different networks also. Okay, very high level. Don't need to worry about what it is. Okay, now let me see whether there are any questions there on the exactly half an hour gap. So if I miss anything, okay, no problem. So let me, here there is one more white paper. If you are interested, you can read about it. What is CUDA? Okay, Compute Unified Device Architecture. This is just to give you how GPUs are used for AI processing. What happens is, normally I told you that we have CPU working with the main memory, right, which is a DRAM, which is on the motherboard. Now, when you have a graphics processing unit, a GPU, the GPU is always built in with some memory inside. Okay, the GPU chip, I will say that the whole thing is a GPU chip. They have a built-in memory inside the chip itself. As I told you, memory coming closer to the processor. That is the one category, very important thing about the GPU. Whereas if you see, CPU and memories are different chips. This is another IC, this is another IC, and they interact over the bus, over the motherboard or whatever. Whereas GPUs, the whole chip has all the ALUs, apart from they also have memory built in. Now, when you have something which is closer to the CPU, the access time is faster, and you can run the clock at a very high rate, okay, nanoseconds or even much more, because the length is very less, so that noise introduced, all that will be preserved. There won't be much of noise, so that we can access it and run the bus at a very high rate. That's the beauty of bringing the memory closer to the CPU. Okay, so GPUs have memory very close to them. What happens normally when you are submitting jobs to the GPU is, the data which the GPU is supposed to operate on is copied into the GPU's memory first. That is what is called copying the processing of data. One, then instruct the GPU, okay, to do the job, and you will be saying what instructions, okay, what code or algorithm to run. That will be given by the CPU. CPU is the master, and normally GPU is the slave. Okay, so master runs when it is encoding the code, it knows that some part of the code is GPU centric. Okay, they are all, even the floating point operations are done by Intel like this. Whenever floating point instructions are there, they are given to FPU, floating point unit. Similar thing is done whenever GPU instructions come up. CPU does not do anything. It will only pass it on to the GPUs to perform the job, because CPU does not understand even what is the GPU instructions are. So the instructions are fed to the GPU, but for that to operate on the data, CPU has to give the data, because CPU has a control of the hard disk and other things, because OS is running here. So CPU is still the master, and it has the graphics data or AI whatever training data. It copies them into memory of GPU and then gives the control to GPU. So GPU does the processing in parallel. So CPU can go and do something else while GPU is processing it. So there is a parallel processing happening in the GPU. And then once the GPU is done with that, it will copy the result back into the main memory, because CPU can access only the main memory. It cannot access the GPU's memory directly. Okay. So you may wonder, how is the transfer done? That is called DMA. If you guys know in the hardware, DMA, which is direct memory access. So normally there is another hardware, DMA, which is programmed to copy from this to this without the CPU's involvement. So CPU programs it and leaves it, and this data is copied here. Similarly, when the results are put, GPU puts the result and the DMA copies it back. So remember one thing, they cannot access each other's memory, but there is another hardware which takes care of copying between them. So this is how this is done. The CUDA is an architecture, an API. Okay, it's a software API associated with the hardware implementation down. CUDA. This is NVIDIA's API. It is similar to GCC of tools. It is it's a set of tools and APIs similar to GCC in the C world. Okay, if you are writing a GCC compiler, linker, and other tool set, similarly CUDA is something for graphics processing. Okay, that much knowledge is enough right now. Don't bother too much. I hope this philosophy you understand how it happens, because when you learn about TensorFlow, it will ask you whether you want a TensorFlow with a GPU enabled or only CPU. Okay. If you are running on a hardware which has got a GPU in it, then you have to choose a TensorFlow with a GPU capability. Then the hardware will be used. If you don't have a GPU, then TensorFlow with CPU will be done. So same operation will be done on the CPU itself, but it will be slow. It won't be as fast as GPUs. Okay, that's why I am explaining you that you understand what is happening underneath. Okay, now I'm sorry. This. Okay. Now let me explain a little more about AI in cloud. AI, you know that there are training phase and inference phase. We train the network and then we use it, train the network, we use it for inferencing. You know that training is a highly CPU intensive and it takes more time to train the network. Inference is a real time. When you have the data, you are making the trained network to deduce what has been trained on. Okay, like recognizing a cat image or whatever. Now, this is one way of what operation is done is here. Where it is running is given in the column. So column shows you what is running on the data center or a cloud, what is running on the edges. Now, training is run always on the cloud for sure. Okay, training can be done, has to be done, because it needs more power and big data, and cloud and the data centers can manage it. High performance computing, you can do it. Inferencing, of course, you can do it on the cloud also, because it is less intensive, compute intensive compared to training. So that can also be run on data centers or cloud. Now, what about edges? This is talking about edge. That means edge devices. Maybe if you have a IoT device, it can perform the inferencing job, because you want, when you have install a CCTV camera on a bank, and if you identify somebody suspicious, this camera and the IoT device in the bank should immediately be able to detect and then alert the bank employees, rather than waiting for the cloud to come back with the result. And in case if it is not connected, then it will be a catastrophe. So inferencing once you train the network, you put it in the IoT devices, inferencing can be done on the edges, okay, for sure. So that is a low power because it needs to be real time. It should not take wait for days. It should come up with the result immediately. So inferencing can be done. But can the training also be done on edges? That is a question mark, which is not doable because of not available. No, you don't have a high power devices or power. You don't have that much of power on the IoT devices to do the training because it is very compute intensive. That's why on edge devices or embedded devices, we don't do a training. But right now, what is happening is slowly coming down. Though AI in cloud on edge are merging. So that's what I'm going to talk about now. Cloud AI processing mainly emphasizes the peak performance, and memory bandwidth and cost are high, requirements are high, and more accurate it needs to be. Lots of parallelism is there, and amount of volume of data is very high. Okay, that is what will happen when you are training a network, and this is what is the cloud AI is supposed to be able to manage. GPUs and FPGAs and AI chips are used for that purpose on distributed cloud service. Whereas on the edge AI, when you run a AI algorithm on edge devices or IoT, the processing mainly focuses on the energy efficiency. You have to be very careful that you don't consume more power, you don't consume more time, because the response time has to be faster. Of course, you have to be efficient, and cost is also a major constraint. You cannot have a very high-end devices on the edge devices. So, and privacy issues, because anybody can tamper with that. Cloud is well protected against cyber attack, but edge devices are not. So privacy issues are there. So they are all the constraints for the AI devices which is running on edge devices. Okay, AI algorithm running on edge devices. So I hope you understand the difference in the way these two operates. Okay. Now there are present collaborative pattern. That means cloud and edge devices work in tandem. That means training is done on cloud and the inferencing is done on the edge devices. Okay, they interact with each other and they work with each other. Okay, that is what called collaborative working of cloud and edge devices. With the increasing capability of edge devices, that means more and more powerful processors are coming up now. More of computing is offloaded to the edge devices. Okay, this is in the it is going on. It's not complete, but because I'll tell you one more reason why edge devices need to be intelligent, because in an autonomous car you have to take decisions instantaneously. If some obstruction is coming or if passers-by is crossing the road, you need to stop the vehicle. You cannot wait for the cloud to respond or the action. So response time is very, very critical in the edge devices. So you need to have that capability in the autonomous car. That's why it is not coming up very easily, because it has a lot of challenges. So the collaborative training and inference among cloud and edge devices will be an interesting direction to be explored, which is going to happen. Okay, I hope you understand the high level what is the difference between cloud AI and edge AI. That's my intent of this slide. Now, okay, I told you that memory needs to be closer to the processing unit for that to operate much efficient way. So what is being done now is memory is interfaced closer to the processing unit. Okay, whatever GPU or AI neural networks, whatever. Okay, they are brought very close. Whereas this is how a typical CPU architecture looks like. Okay, this is the system bus and memory is a separate chip, and they interact over the system bus. This is what you are already aware of. Now what you are learning now is processing is also done in memory. Okay, that is the direction in which AI chips are moving in. So in-memory computing signifies a fundamentally different approach compared to von Neumann architecture. Von Neumann architecture is what our normal CPU architecture is all following, where the memory is different, CPU is different, and CPU keeps accessing the memory and processes it and puts the result back into the memory. Whereas here, in-memory operations are done. Okay, just understand this difference. Okay, that is enough. Recent advances in the area of demonstrated that the capability of logic operation as well as neural network processing. So even logic operation means and or operation, and neural network processing like matrix multiplication and all that can be done in memory operation. Okay, by keeping the data in the memory without even bringing into the CPU or the processing, you do it in the memory itself. Suppose what I mean by that is, suppose you have two matrices need to be multiplied and the result has to be put. You don't bring the matrix here, multiply and put the result back. You do it keeping it in memory. Okay, just in simple term, this is what in a high level happens. Okay, so what you gain by that, you don't need to transfer the data quite often from memory to the processing unit for the processing. So that removes the delay. Okay, that's why it is able to do much faster. Okay, now I am not going to go into the details. You can read through it later on because it has got all the AI terms in this. I am showing you here this only for you to go through it leisurely and see where which belongs. Okay, this is the whole stack. Okay, everything works together for our AI to happen on an IoT device especially, or even on the cloud. But what technology improvements in each level has made it possible is what is given here. I want you to run through it leisurely later on, not in the class, during the class, but just spend some time. Try to at least understand, Google about these acronyms, try to understand it a little bit so that you have a complete picture of what you are learning. You can even map whatever you are learning in different courses in this program. You will be able to map it to which layer it is. Okay, a complete picture is always good so that you can relate what is happening. Okay, I'm not going to the details. We will do it later on when the time comes, if it is required also. Okay, now this is another just a marketing slide saying that NVIDIA is working with different vendors on different areas. Okay, don't bother. You don't need to. I'm not going to ask questions on this. This is just to give you how well the AI is spread on different areas. Okay, that's the beauty of this. So now what is happening is developers want to create AI solutions anywhere and deploy anywhere. Okay, that is why we are all learning AI on IoT. So NVIDIA GPUs are available on all platforms: desktops, notebooks, servers, and supercomputers, and even for IoT devices. They are running on cloud. Okay, NVIDIA's architecture is running on Amazon, IBM, Microsoft. Okay, all these AI cloud platforms, AI platforms of this, they all run on GPU. Okay, but different versions of NVIDIA's GPUs. So they made a lot of changes in the NVIDIA's framework, and working with internet companies as well as research and startups and all that. Now they try to improve it for different platforms, different purposes. Either it is for both cloud as well as on edges. Now they have GPUs for different form factors. What is form factor means? Dimensions. Okay, form factor means what is the performance. You may need a smaller version for the IoT device. Okay, same NVIDIA GPU with a low power device with reduced features will be available for IoT, whereas for the cloud, same NVIDIA will be supporting or supplying the chips for it, cloud. This GPU will have all kinds of features and very power hungry, and it can take more data and they can operate. So the same family of GPUs are also available for IoT edge devices as well as for cloud devices. So the same like Intel's processor, you have processor which is running on embedded devices. They also run Intel architecture as instructions, whereas the supercomputers or even the big multi-core processor also running the Intel instructions, but they are different. Okay, they are meant for different purposes and they consume different power. So that's what is the same thing is done in GPU also. GeForce is for PCs. These are all brand names from NVIDIA. Tesla is for supercomputers and cloud. Jetson Nano, which I will show you. They are meant for robots and drones. Drive PX is another chip platform which is for cars. Okay, so they are all from NVIDIA. They all follow the same AI architecture, modified GPU, but for different purposes. Okay, that's what I'm trying to tell you. All of them share the same architecture and accelerate deep learning. So that's the crux of it. Don't worry, NVIDIA is working with different companies, and higher education is what is the majority of them, and there are 3,500 companies or industries they work with. So major applications, there are many applications: automotive, robotics, entertainment, everywhere AI is there. And autonomous car is the most important place wherein what you learn in the IoT course will be useful for. And you know that NXP, Qualcomm, a lot of companies are working on making chips for this autonomous car. And if you want to know, okay, how actually autonomous driving is going to evolve, please read through this interview by the CEO of NVIDIA. Okay, very interesting, very thought provoking. Where is the future for autonomous driving is given here, and these are the different levels of autonomous. This is completely fully autonomous. The levels of autonomous cars. This is driverless. It can complete has control, whereas this is level 2 is partial control with the AI and the driver, and these are all different levels. Okay, I'm just giving you a very higher level. Then normally when you listen to Qualcomm CEO or somebody talking, they say that the chips are made for level 5 kind of autonomous driving car. So you will understand what is level 1 and level 5 is all about. And please read through this interview. It's very interesting. Okay, this I think I want to stop here. I think we have exactly at 50. You may feel that I went a little fast, but the material is just to give you an introduction and feel of where the AI area is going out and how different architectures are used for that purpose. Okay, so I thought of showing you a real NVIDIA chip, but I felt that it will be too much to digest now, so I am not showing you right now. Maybe when we learn more, we can. If you are interested, I can show you, and we can spend some time on that also. Okay. Any questions or anything, guys, from any one of you? We can discuss that. What I plan to do, let me tell you. General purpose graphics card like RTX or GTX series NVIDIA or commercial graphics NVIDIA, which one is used for AI? You cannot use them directly. Okay, GTX or GTX, they meant for different. Yeah, that's what I feel. Maybe I can Google and find out, or you can also do it. But see, they're all application specific. Okay, you cannot randomly run a unless. Okay, let me explain you. Maybe to give you one just overview. Suppose RTX GTX is there. Okay, this is something a hardware framework. Okay, or hardware GPU architecture. Now your software, you have CNN or DNN, something you implemented, you want it to run on this chip. Okay, who decides it? It is the NVIDIA. They decide it. Okay, if suppose they have provided an API or some way of porting this to run on this hardware, it can be done. Okay, but as you understand, we cannot change the architecture of RTX or GTX after it has been shipped to the individuals or consumers. So unless there is a software support to port or run your network on this, it is not possible. Okay, whether they have done it or not, even I am not aware. But if it is meant for it, then they should take care of it in the hardware, and then they should also provide whatever the CUDA interface or whatever they need to give it. Then only you will be able to run it. Okay, it is like this. Suppose if I have a CPU, you and me decide some CPU instructions, and then we come up with a new CPU. Okay, IEEE IEEE Lucknow CPU. Okay, unless we give the tools, compilers, linker, and all the tools for our chip, which translates the higher level language to the assembly program of this chip, we cannot run it on them. Okay, so similar to that, RTX GTX is a hardware and platforms which are meant for gaming, because lots of gaming platform they have provided, and it has been already ported onto this chip, so it can run. But if you want to run any AI algorithms, it should have been supported by the tools vendor, otherwise or NVIDIA or some third party should have done it. Otherwise, it's not possible. Okay.